Okay, fifth years, just wanted to run through a couple of notes on what you guys did earlier on in the week with me when we talked about levers, moments, and so on, things like that, and then tying in with the mandatory experiment. A lot of people had a couple of issues with that, so I wanted to run through an exam paper question just to see the setup, what kind of things are asked, and how to go about it to make sure people are a bit clearer on it. I know the experiments kind of emulator that you guys attempted was a bit finicky and wasn't the easiest thing to use, so I just wanted to run through an experiment question to make sure you're clear on it. So first bit then, I'd ask you to look at a couple of diagrams about our moments and the force and distance. So I've just drawn a quick example of the door one. You can imagine if you're trying to open or close a door, you use the handle, nice and simple. And the reason for that, and the reason that the handle is in that position, is because it's far away from the fulcrum. In this case, they are the hinges on the doors. So the further away from the fulcrum, the higher or the larger amount of force that we can apply, or the bigger the moment we can apply. You can imagine if you've got a heavy door in front of you and you're trying to push it closed, and you push at that section of the door that I'm just marking there, if you push along that line, it's going to be really, really hard to close. If you push from where the handle is or on that side of the door, it's going to be much, much easier because the force that you apply is further away from the fulcrum or further away from the center or the turning point, which means that the force that you apply produces a greater moment. As we said, it's going to be force multiplied by distance. So we're talking about newtons multiplied by meters, not centimeters. So make sure that we convert it into meters, and you end up with Newton meters as your unit, which is our unit for the moment. Okay. When we tie that in, as we said, with the idea of equilibrium, then we are trying to find a balance. So when we talk about equilibrium, it looks like the word equal, as you've talked about. If people who are doing chemistry as well will talk about equilibrium of a reaction and how the products and reactants find an equilibrium where there's a certain amount of one thing will make a certain amount of another. So when we tie the idea of equilibrium, it's balance essentially that we're really talking about. And we want to discuss that and look at a few bits on that now. So the idea of equilibrium, as we said here, we've got the sum of the forces in opposite directions are equal, and the sum of the moments about a specific point are equal to zero. So for the first one there, the sum of the forces in opposite directions are equal. So you can imagine if you are pulling something or pushing something, that they're going in opposite directions to one another, they are equal. Nice and simplest example of this, you can imagine if you've got a seesaw and you've got two twins that have got the same mass and they're both sitting on the seesaw, then, or standing on the seesaw in this diagram, then it will be balanced, or it will have reached equilibrium, because if this guy is 50 kilos and his twin brother is the same, and they are standing the same distance away from the fulcrum, which is that point there, that distance and that distance are equal. Let's just call it x, for example. So that's x and that's x. It means that the moment is the same, the force and the distance. Force is equal, distance is equal, which means the moment is equal, and we've reached equilibrium. Now, if one of those change their position, or if they grab a hold of something and increases their mass overall, then we're going to have a change, and the equilibrium is not going to be matched, and we're not going to find equilibrium, or we'll find equilibrium, but it'll be in a different position, and we'll end up with one person up that way and the other person down there. So that's what will happen when we change the circumstances. When with the second one, you can see the sum of the moments about a specific point are equal to zero. So I've got a quick diagram drawn down here, and we're going to tie it in with the idea of a couple in a second. But you can imagine the sum of the moments about a specific point are equal to zero. In this case, we'll go back to the seesaw. This is our specific point, the center point, the fulcrum. And the sum of these points about a specific point, the sum of these moments. So you can imagine we've got a downward moment going that way, and a downward moment going that way, they will be equal to 0 because they're going in opposite directions to one another. And we combine those, one positive, one negative, and they will be equal to 0. When we talk about the idea of a couple, as we said, I've written there, two parts working oppositely to improve the ease of movement to something. So the example there I've got is like a tire brace for a car. If you're trying to change a wheel on a car, you can see that we pop that section in and it goes around the nut on the car, or around the bolt on the car I should say. And then if we turn it clockwise or anti-clockwise, in this case we're turning it clockwise, the same way as the arms go on the clock, then it will hopefully start to turn, and hopefully we'll be able to loosen the wheel and take the wheel off. But you can see I've got one part going one way, one part going opposite to that, but they are both working together to do the same thing. Even though one's going one way and one's going the other, when they're both acting, then it means that we're making it easier for that bolt to be loosened and to be taken off of the wheel. The example that's given to you in the book is nice and simple as well. You've got the concept of a tap. You can imagine you turn a tap on and off that's got like an X shape on it, and you turn it that way, you turn it one way, or you turn it the other to turn it on and off. Nice and simple. Same with the handlebars on your bike. If you push up with your left hand, the bike is going to turn right. If you push up with your right hand, the bike is going to turn left, because we're going opposite to the direction that you are applying that force. So the wheel turns and it makes you go in the direction we're talking about. So to tie those in then, and the idea of equilibrium, we've got an example here. This is question 1. This is from the 2014 ordinary level paper. So 2014 ordinary level. I wanted to do an ordinary level one because I didn't want to phase you too much, and I didn't want you to be able to attempt the higher level one on your own and see how you go later on. So you can see here we've got student investigate the laws of equilibrium for a set of coplanar forces, and they're acting on the meter stick. The weight of the meter stick is 1.5 newtons, very important, and the centre of gravity was at the 50 centimetre mark, very important. The student applied the forces shown to the meter stick until it was in equilibrium. So we've got forces acting upwards, forces acting downwards, and I have that other one, the weight of the meter stick. And you can imagine the weight of the meter stick at the 50 centimetre mark is also acting downwards. So how did the student measure the upward forces? First and foremost, how do we mark this? If you look back at your experiment, we know we've got our Newton balances there, okay, to do it with. I've got the marking scheme on the next slide, and you've got your Newton balances there, okay, and you can see it there for 4 marks. It says copy the diagram, show all the forces acting on the meter stick. So the only things that you have to add to this one in this case, so you got our diagram there, and I'm able to annotate over it luckily instead of having to redraw the whole thing. So you can imagine you'd need to redraw that, pop in everything that you've got. The only addition that we've got there is that 1.5 newtons, the weight of the meter stick. And as we discussed, that's pointing downwards. So at the 50 centimetre mark, we'd make a little arrow like we have done for all the rest, and we put in our 1.5 newtons. And that's all you'd have to add to that diagram for another 6 marks. You can see there's nothing else added to it there, nice and straightforward. Okay, the next part then, it's asking for find the total upward force, the total downward force, and explain how these verify one of the laws of equilibrium. If you remember, we've talked about the laws of equilibrium there already. Okay, so we've got our upward forces and our downward forces. Our upward forces are these two pointing upwards, shock horror. So 9 and 12.5 giving us 21.5 newtons. The downward forces, 1, 2, 3, add those together, also 21.5 newtons. and explain how these values verify one of the laws of equilibrium. We go back and we can see the sum of the forces in opposite directions are equal. So they're in opposite directions. I've got the upward ones and I've got the 3 downward ones. They are opposite to one another and they are equal based on our calculations. Done for 15 marks, nice and straightforward. And then finally, our sum of the anti-clockwise moments of the upward forces about the 0 mark, and the clockwise moments of the downward forces about the 0 mark. So this is the important thing to keep in mind with these. And I'm going to go straight to the marking scheme to show you this before I do another multiplication here. About the 0 mark. And I'd say that that's where people might have been tripped up on doing any calculations you guys did already. Remember we talked about our moment earlier on, force by distance up here. We did force by distance. That's what we have to do now. But we're doing it about the 0 mark. We're not doing it at the fulcrum. We're doing it at the 0 mark. So we have to be careful about this. So let's have a quick look. Okay, and sometimes it's a bit counterintuitive, but we'll take our time and we'll get there. Okay, so you can see the anti-clockwise moments of the upward forces about the 0 mark. So you've got the 9 by 0.2, and we've got 12.5 by the 0.9. So if you think about these, let's go back to the bigger diagram. You've got the 9 newtons and you've got it at the 0.2 mark. This is our 0 mark on the diagram. That looks like a 9. Let's go again. That's a 0. That is the 0 mark, okay? It is 0 centimeters on our meter stick. So that's the 0 mark. Force by distance. 9 by the 20 centimeters in meters. Remember we discussed. So that's why it's 9 by 0.2. The next one. 12.5 by 0.9. And that's why, or that's where we get those values from. So you can see that then in the marking scheme, the 9 by the 0.2, the 12.5 by the 0.9, add the two of them together, we end up with 13.05, and it's Newton meters. Remember, force by distance, Newton by meters gives us Newton meters. So we got 13.05 there. And again, it's Newton meters. The next one, the clockwise moments of the downward forces about the 0 mark. So it's telling you which ones to do. Remember, I wrote that one out, so we need to make sure we go back to that. It's 1.5, isn't it? I get rid of the upward ones for now. So I've got, that's our 0 mark again. We've got force 5 by distance, and that's 0.36 by what I can see there. So we've got 5 by 0.36. We've got the 1.5, which is the weight of the meter stick, and that's at the 50 centimeters mark, if you remember. So that's 0.5. And we've got the 15 newtons at 0.7. 15 by 0.7. So they're the 3 downward forces, or the 3 clockwise moments about the 0 mark. Now I need to explain that again. Look, you've got 5 by 0.36, 1.5 by 0.5, and the 0.7 by the 15, and that gives us 13.05. Again, I'm very happy because that number and that number are equal. Now, the thing that people were getting mixed up on, I think, more so than anything else, with the idea of clockwise and anti-clockwise. So let's clear this once more and let's explain that in a bit more detail. I'm going to leave those values there just to make sure, and we can see how those numbers relate to what we're talking about. So let's look at those clockwise ones. We are clockwise moments of the downward forces about the 0 mark. So we've got the 3 clockwise moments. Imagine, about the 0 mark, they are moving in a clockwise direction. From here, that is going clockwise. the weight of the stick is going clockwise, and the 15 newtons there are going clockwise. They are moving in the direction that a clock would. So that's why they are the clockwise moments. The anti-clockwise ones are the ones going upward, in this case, about the 0 mark. Anti-clockwise, anti-clockwise, opposite direction to the way the clock moves. Now, at higher level, you will be asked to do that a little bit differently. In ordinary level, they do it at the 0 mark, is nice and straightforward, because you're going up and you're going down and they're clockwise, anti-clockwise, that's fine. You might be asked at the 50 centimetre mark or at the 80 centimetre mark, for example. So you can imagine, if I'm at the 50 centimetre mark, let's just make it a little bit easier. At the 50 centimetre mark, I've got that one is going clockwise. That one is going clockwise. But that one is going anti-clockwise. That one's going anti-clockwise. So we have to be a bit more careful. Now, that, again, that's for a higher level question, so you'll be able to do that later on. But that's all there is to it. And at the ordinary level standard, nice and straightforward. Question asked then to finish off that, explain how these values verify the other law of equilibrium. Remember, we had 13.05, 13.05. Moments are equal, or the sum of the moments equal to 0. Same as we discussed here, the sum of the moments about a specific point. The specific point in this case was the 0 centimetre mark, or at the far end of the meter stick, which is here, okay? So the sum of those moments were equal to 0. So keep that in mind. Hopefully that makes it a bit clearer for you, and you've got a couple of calculations based around what we've discussed there to try and do, and I'll give you an exam paper question to do on that then later down the line. Thank you very much.